Hello, in this lesson I'm going to talk about Laplace transforms. Laplace transform, this concept, it's used a lot and it's very useful for engineers, especially control engineers and electrical engineers. It is not only used to solve differential equation, but also to transform one function from one domain to another. This is the equation of Laplace. This L denote the Laplace. So Laplace of a function of t, Laplace a function of t is equal to, and that's what you apply to get the function of s. That is the end result. So fs here is already transformed. So you start with a function of time, or f of x, and you transform this into a function of s. So you start with ft and you finish with fs. Okay, so f of s, it's the transform of f of t. And later on in this lesson we're going to find also the inverse Laplace transform of f of t, inverse Laplace f of t, gonna give us the f of s. Let's do this example. So we've got a function of x. That is the definition of Laplace. That is the definition. So basically you can start from f of x. You take any function, to transform it you multiply by this e to the power st, e to the power minus s x, or xt, and you take the integral, you multiply it by the function of x. Let's start with a simple example. In this case we have a function of x equal to 2. What is the Laplace transform? Okay, so the way to do it is, that is the Laplace transform of 2. Look at these parentheses, and that's going to be equal to this integral going from x equal to 0 to infinity. Then you multiply the original function we've got, which is 2. You multiply by this e to the power sx, and with respect, you integrate that with respect to x. That's the variable now. It's a function of x. Or if you have a function of t, it's going to be a function, a d of t. You integrate, and when you apply the limit between infinity and 0, you should get 2 over s. Just pay attention to the condition here. The integral must converge to a value, to a finite value, and that's what it says basically here. So s has to be greater than 0. Now we can do another example just to make this more clear. So in this example we are trying to find the Laplace of the Laplace of this function e to the power kx, the Laplace transform of e to the power kx, where k is a constant and x is the variable. So we integrate this function. The original function, which is e to the minus kx, we multiply it by e to the minus sx, and we integrate with respect to dx. The boundary condition going from 0 to infinity, and we're gonna finish up with this term here, 1 over s plus k. Now, following the same procedure, we can get a whole set of Laplace for a variety of functions, and these usually available in tables, so you don't have to actually derive each function as you go on. you just use the tables available for different functions to give you different Laplace transforms. And this is an example of such table. On the left here you can see the function of x. Number 1 is the transform of 1, and that will give you the Laplace transform, which is 1 over s. Not very clear, but you can see it. And this is done in the same way we've done it, and this is one of the function we've done just now, e to the power of some kind of power kx, and that gives you the Laplace transform on the right here. That is a clearer example. This is given in on your bright space. You can see this table. It doesn't include all the functions, but these are some functions that you can use in the next examples. Now have a look at these two examples and see that you can find the Laplace transforms for these two functions. We will go through this later on another video.